Oh, I think my mic was cut. Good morning, everyone. We are ready. Yeah, I'm ready. And it's an exciting one. Today, we're talking about really, really cool features, really cool tech. But I'll wait 2 more minutes, like usually, just to get everyone on board. And I was saying that this is horrible light, but I don't have another setup here, so I have to do with that. Good morning. Okay, let's go. So today we're talking about two features, two really cool features. The first one is about HTTP outcalls. The second one is about Bitcoin, Bitcoin integration and threshold ACDSA. We'll first start with HTTP outcalls. I'll show you the general explanation of what it is and what you can do with. We'll do some coding example, and then we'll do the same for Bitcoin, for the Bitcoin integration, how it works. And if we have enough time, we'll do a little demo of the Bitcoin integration as well. Okay, so starting with HTTP outcalls, this is a general issue for all blockchains. The issue is how do you get information outside of the blockchain? So you have your contract. For example, on this picture, we're talking about something on Ethereum. You have your contracts that are on the chain. So you can have multiple smart contracts. They can communicate with each other, exchange information. But how do you get information that is outside your blockchain? So how do you get, for example, the weather, the temperature of today, the price of an asset like Bitcoin, the result of a match? All those informations, they are outside. So they are in the Web2 world because we have APIs like a weather API that would provide those informations, but it's not directly on the blockchain. And it has been a really, really problematic issue that's basically made blockchain kind of useless because they are just in their world without communicating with the outside. But there was a solution that came up with the concept of Oracle. So an Oracle chaining is probably the most known Oracle. Essentially, an Oracle is a service which will get information in the Web2 world. So for example, in this case, if we want to know the weather, it's going to call the weather API. And then it will write this information in the blockchain. So in this case, in an Oracle contract. And you as a developer on Ethereum, you will be able to call this contract to get the information on your smart contract. But notice that here, you're basically trusting this intermediary. So Chainlink is providing this as a service, as a company. So if you are using this in your stack, you are basically giving away some ownership of your stack and also some trust in this company. So that's something that you might not want to do if this is like a critical part of your infrastructure. Of course, the IC, so the internet computer also has this issue of canisters able to communicate with each other, but how do they communicate with the external Web2 world? And so they've released a new feature a few months ago. It's very, very new actually, because it was not part of the launch of the network. So for a long time, I've been building on this network and there was not this feature, but they've been working on that. They've been talking about it and it's been released a few months ago and now it's live. It's really cool because canisters can directly make HTTP outcalls to external entity. So as you can see, it's a kind of one-line call. You can write your canister as we are doing during the week. So you write your code and so on. And then if you want to make a call to an external service, you can just do it in one or a few lines. and the canister is able to get information. For example, for this Web2 API, it will get the information directly. And so how does all of this work? It's a native approach because it's integrated into the protocol. So it's not like you have to call an external service or use an external service. It's part of the ICP protocol itself. We can take a look at how exactly it works. So, okay, let's see. Yeah. Remove the chat. So remember that under the hood of a canister, there are multiple different nodes. So what we need to do is to have all the nodes call the API. So if you have a subnet, you have 15 nodes that are running your canister, all of them are going to call the external API. Then they need to reach an agreement because remember, we are on the blockchain, so we need a consensus. And it's possible that all of these nodes, when they are calling the API, they have a slightly different value. So for example, if you're calling the price, like a typical example would be calling the price of Bitcoin. So you have, for example, Coinbase or Binance, they have API where you can call at any time and get the price in dollars, for example. You have to think that each node is going to be slightly delayed or slightly faster than others. And so the price is very sensitive. It's going to move a little bit, yes, like maybe for a few cents or a few dollars, but all nodes are going to receive a different information. And so we need to come to an agreement, which is going to be usually the average value of those nodes. And I'll show you how you can do that. And then once we have the agreements, this is an information that is basically given to the canister. So as you can see, we just do this line, await management canister, HTTP request, and we do our requests. So yeah, how do you reach consensus is the main question. And the main question is quite easy to answer, actually. So essentially, as a developer, you need to provide what's called average function. And so this average function is going to be used so that in most cases, you can reach consensus. So for example, in the case of on the right, so for example, we are querying the temperature. You can use a transformation function that is going to truncate your value. So you would say, I will accept slight deviations of the values if they are in a reasonable range. So for example, in this case, someone has some of the node has 25.25, 27.25, 27.26, 27.24. You can notice that it's not the same value, but it's slightly the same. And so you can define your range and you can say this is acceptable, and the consensus, the general value that we agree on is going to be 27. This means you can have some nodes that are malicious because remember, we are in a consensus protocol. Maybe some of the nodes of the internet computer are malicious, and we need to make sure that even if some of them are malicious and giving false information, we can still reach the true value. And so it's essentially the same as the main consensus. If you have 2/3 of the nodes that are non-malicious, you will reach the correct value. So in the example on the left, we have someone saying that the weather is sunny, someone saying that the weather is cloudy and there is a thunderstorm, and someone saying that the weather is sunny. So the majority is winning. So that in that case, the HTTP request would return a sunny weather. So what's the use case for that? What do we use it for? Well, there is a good example already out live, which is called the exchange rate canister. Essentially, it's a canister that gives us values, certified values. So we can get the price of different assets in dollars or in euros or in other currencies. You could use it for connecting your canisters with IoT devices. So actually, the team that we will receive this afternoon, we have the team of Massimo and Luca. They actually prototyped a way for a canister to control a physical object. Basically, they've done that through HTTP request. You could use it for connecting with Ethereum nodes, or also to connect with Web2 social medias like Twitter, Facebook, Instagram. You could use that for getting information from those platforms. Also more traditional payment system like Stripe, or you could use that for querying like artificial intelligence model. So there are quite a few use cases, and I think that's not all of it. There are way more than that, but that's a good start. So I'll take the question. No, it's not a question. It's just a good morning. Let's go to the documentation. So there is a dedicated page on the internetcomputer.org website called HTTPS outcall, which explains how it works. That's basically what I've said. The Oracle problem is what I've talked about. And if you really want to go even more into details, you have this wiki, which explains the whole architecture of the HTTPS outcall. So how it works, what kind of decisions are taken, what do the node do at each step. So you have all the answers to your question here. What we are interested is the, well, first the example. So I want to show you the exchange rate canister. And I believe it's this one. So this is the exchange rate canister I've talked about. This canister makes use a lot of this HTTP request feature. And you can see that basically we can use this canister to get exchange rates. So the exchange rate is necessary for the system because, so let me see, can I call it? I think I need, yeah, there are a lot of parameters in this. Let's say, so I should be able to get, let's say, I should be able to get the exchange rates between, for example, Bitcoin and US dollar. So I will try that. But the only thing I'm not sure is how do they, what kind of symbol do they use? Like, is it, well, let's see, maybe, so USD and BTC, I guess. Okay, so no, apparently, maybe in capital letters. Okay, so the canister just rejected my message for some reason. Yeah, it's the first time I'm using this canister. But yeah, essentially you would be able to use it. For example, one use case for that would be, so on the dashboard, remember that there is this concept of cycles. So here we have this concept of cycles, which is credit for canisters. And the good thing about the cycles is that we don't want the price of building on the internet computer to depend on the price of the ICP token. So if the ICP token goes down or if the ICP token goes up, you don't want, as a developer, the cost of your application to change. This is what happens, for example, on Ethereum. Your fees are going to go up. On ICP, we have this exchange rate. So essentially, if ICP goes up, you get more cycles per ICP. And if ICP goes down, you get less cycles per ICP. And there is a balance. And this balance requires the system to always know the price of ICP. And so essentially, this is making use of the exchange rate canister that we've seen. The exchange rate canister, unfortunately, is written in Rust, so that I'm not going to dive into the code today. But if you're interested, the repository is here. Now, what I want to do is go to the dev documentation, or maybe actually, yeah. So this is a Motoko example of how to do it. And let's dive into it. Okay. So let's go to the playground. This is how you can import a repository in the playground directly. So I'm just going to copy the name here. And this should, okay, yeah, this imported my canister. Let's see if we can deploy it. Okay, so looks like we've successfully deployed the code. So I've just imported it from the GitHub repository. You can do that easily from here. So you have the examples project, but if you go here, you can import any repository by just specifying which repository, which branch, and which directory. And now let's try it out. So we should get the ICP USD exchange. And to do that, okay. So this is not working because I believe I am in the playground. And okay, yeah, that's not fun. So the playground has some limitations because we are not paying for that. And making those calls needs and require some amount of cycles that we don't have. So let's still go through the code, assuming that it would have worked if we were on the mainnet with no playground. Essentially, what I wanted to talk about is this syntax. What we do is we call the Internet Computer Management Canister. So this is inside types.mo. You have this management canister, which is essentially a fake canister. So this is a canister that doesn't really exist, but it's provided as an interface of a canister so that you can call it from your canister and you can call like functionalities of the system. So for example, that's how you would get HTTP request. That's how you would get threshold DCDSA, which we will talk about later. And there are a lot of other features. I can actually show you all the features that the management canister has. It's not here. Let me see. Management canister. Not this one. Okay, so I know that I've already used it in the past. So I'm going through my previous code. Yes, here. So this is the type of the management canister. And so with this canister, you can create other canister, update the settings of other canisters. You can install code into other canister. You can deposit cycles. You can check the status of other canister. You can change some settings, and you can do those HTTP requests. So the management canister is a very important concept, which I believe is not documented enough. But essentially, yeah, it's like an interface for you to call system functions. And so we need this this management canister. So that's what we have this line here. Then we need some arguments for the HTTP GET request. For example, we need the host, we need the URL, which is here. We are basically calling the API of Coinbase. We are specifying our request headers. And this is where we need the transform function. So the function I've talked about in the slides, the one that essentially would average all the results. This is here that you see it. And it's essentially here that you define it. So it's currently kind of low-level functionality, which means that you kind of need to write those transform function yourself, depending on which API you're calling. But you have a lot of people in the community that can help with like which function and how to set up your function, transform function. And we are starting to see some libraries that kind of abstract away the transform functionalities. Then you need to add cycles. So this is where the code is failing, because I'm in the playground, and in the playground, you don't have access to this functionality. So I cannot add cycles. This is prevented because cycles, as I said, are real credits. And if I could take cycles, I could empty the playground, steal some cycles, so essentially steal money. So that's why it's restricted in the playground. Then you make the request, you decode it, and then you can return it. So here, and I wish I could have shown you, but yeah. So do we have any question with the HTTP request so far? I believe that there is another example here. It's the same example, yes. So you have the Motoko version and the Rust version. I'll send that in the chat. So of course you have the get, so the get method of HTTP request, but you also have the post method. And for the post, I've actually never used it. But yeah, apparently you can post content. And if you're interested, it's also the tutorial is also here. Post requests are even easier. The only problem is that you need to prevent the fact that when you do a post request on the IC, multiple nodes are going to do it. So you could receive multiple times the same request at your Web2 server. So you need to add protection for that. There are some ways to prevent that, but essentially that's what you need to take care of. Okay, so let's go to the second part of the talk, which is about, let's remove that. Okay, so this is about Bitcoin and how it's more than Bitcoin, because actually it's very, we could do the same. What we did with Bitcoin could also be applied to other cryptocurrencies, but the Definitive Foundation and the ICP community decided to go forward with Bitcoin as the first example, because this is the biggest like crypto in terms of users and liquidity. But essentially, it answers the question of how do you bridge the gap with other ecosystems. HTTP Outcodes is about how do you bridge the gap with the Web2 world. And this feature, so threshold ECDSA, which I will explain, is about how do you bridge the gap with other ecosystem, but other blockchains. So also, it has been a problem overall in the world of blockchain. The problem is the following. Imagine that you have, so you are the person in the bottom with the red cap, and you have some Bitcoin. So that's what you see on the right, you have some Bitcoin. But you want to use that on Ethereum. So you want to use that with some Ethereum applications. For example, I've listed Uniswap and Curve. Those are two big DeFi applications on Ethereum. But you are a Bitcoin user and you only have Bitcoin, you don't have Ethereum, and you would like to use your Bitcoin because you want to keep them. And you don't want to necessarily buy Ethereum, but you want to use the applications that are on the Ethereum network. So how do you kind of solve this problem? There is the concept of bridge, which is essentially what we use today. So that's what you see in the middle. A bridge enables you to bridge your assets from one network to another one. The problem is that your Bitcoin lives on the Bitcoin network and it has no real value or no real existence on the Ethereum network. And so to bridge that gap, you have the concept of a bridge. A bridge is an entity that controls a wallet and a smart contract on the other side. So you can see that basically you're sending your Bitcoin to this wallet. Once it is in the wallet, in the control of the bridge, so the bridge is usually a company or a consortium of company. Once they see that you've sent your Bitcoin, they will emit something called wrap Bitcoin on the Ethereum network, which essentially is a copy one-to-one. And you can use this wrap Bitcoin because the wrap Bitcoin lives on the Ethereum network. And then you can send it to Curve smart contract. You can do things on Uniswap, all sorts of things. And yeah, so essentially the bridge controls the wallet and the contract on the other side. And they make sure that you always have a one-to-one relation between how much Bitcoin exists in their wallets and how much wrap Bitcoin they have created. If they create more, then you have a risk, because essentially it's a possibility that not all users will be able to get back their funds. And the Bitcoins are always more valuable than the wrap Bitcoin because those are the true one. And it's an example with Bitcoin and Ethereum, but you could replace with any network, any blockchain would be the same. And we can actually maybe take a quick look. So I believe that's, so yes, of course, this is like a market cap. So this is like a recap of all the crypto. We have Bitcoin and we have something called wrap Bitcoin here. I don't know why it's not loading correctly, but let me refresh. Yeah, so here. And this is essentially Bitcoin on Ethereum. You can see that you should have a smart contract here that corresponds to the the smart contracts that creates and burn those wrapped Bitcoin. So we've seen a lot of hacks and a lot of problems with those bridges. So some of them are more reputable in the sense that you have big companies behind. So you have usually Binance or Kraken, big exchanges that kind of make sure that it's secure and safe. But still, you are trusting them. And the problem is that most of the time, the company behind the bridge is not really experienced or reputable. And so you usually have a lot of hacks. People lose their fund. They got stuck in one network. They cannot bridge back to the other network. And it's also not very convenient for users to do that. So yeah, bridge has been a huge problem in crypto. So how does DIC tries to solve this problem? Well, the same way that they are trying to solve the problem of oracles with a native approach. So it's not a magical approach. We still have the problems of networks are different entities. But we have something super cool, which is on the internet computer, canisters can receive, hold, and send Bitcoins. And I mean Bitcoin from the native Bitcoin network. Oops. I think I have a version without the animation. Let me show you because it's all good, those animations, but yeah, until it gets boring. So, okay. So what I mean by that is that a canister can have an address on the Bitcoin network. So it can be essentially a wallet, like any other wallet, and it can also sign transactions. So there is a connection directly between the ICP network and the Bitcoin network. How does it work? So we have on the right the Bitcoin network, on the left the ICP nodes, and essentially some of the nodes on ICP are directly connected to nodes from the Bitcoin network. So they communicate directly. And every time there is a transaction on the Bitcoin network, the transactions is going to be stored on the ICP network. So essentially there is a copy of the Bitcoin network on the ICP network within what's called the Bitcoin canister. So it stores all the ATXOs and all the balances. Yeah, that's how it works. And then your canister is able to call this canister to make like calls to the Bitcoin network, so you can get balance from your canister, you can sign transactions, and so on. That's the first part, because when you want to connect to networks, you need to make sure they are synchronized. But the second part is the most complex, is how do you sign transactions? Because to sign transaction, you need keys. And how do you make sure that your canister can hold keys in a safe manner? That's the big problem. So most of you are probably familiar with this, but quick reminder for everyone. Cryptocurrencies use cryptography. We have this concept of public and private key. So how you create a transaction on Bitcoin network is pretty easy. You create a transaction by sending instructions, so a transaction, and signing it with your private key. So that means that if we want to create transaction on the ICP network, we need to have private keys stored somewhere. But of course, we don't want one node to store the private key, otherwise that would not be safe. We don't want users to store their private key directly. So we need a way to kind of safely store those private key. And this is called threshold ECDSA. So remember, we have all those nodes in a subnet. Essentially, the private key is divided into shares, and each node is going to receive a share of the private key. When you do that, to create a signature, you have to go to consensus. So it's part of the ICP consensus, and every round, if you want to create a signature, you have to go to consensus. You need at least 2/3 of the nodes to reach an agreement and to sign the transaction. It's very complex topic. We can I will send you documentation if you want to read more. There are like really, really good videos and talks with the cryptographers that explains how it works in more details, but essentially the private key is never reconstructed in this case. So no one ever owns the private key, the full private key. So not the nodes, not the protocol, not the users. The private key is never reconstructed. What it means is that we have connected two networks. So essentially, the nodes are going to load the blockchain. They also broadcast transactions, so there is a two-way connections. They choose random Bitcoin nodes, so they make sure that they usually talk with all the nodes that are available. There are more than, I think, 10,000 nodes in the Bitcoin network. So they regularly change and shuffle which nodes they connect with to make sure that it's as decentralized as possible. They sync the network in this Bitcoin canister, and then you do intercanister call to essentially connect with the Bitcoin network. So you can check balances, create transactions, send transactions, request signatures, and so on. You will notice it's not so different, but it is. It's basically natively integrated. Instead of having to rely on an entity like a bridge, you integrate that at the protocol level. And so it's not magical solutions. There are also trade-offs with this. For example, you need to make sure that you have enough nodes in the subnet to essentially guarantee the security of the key. You need to make sure that this Bitcoin canister is correctly synced to not have delays when you send transactions. But if it's done properly, it's a cleaner integration than other networks, because you don't have to go through a bridge. You essentially have two networks interconnected. So it's, I would say, more beautiful and simple in the overall scheme of things. Now I want to talk about I want to talk about something called chain key Bitcoin, which essentially uses this underlying technology that we've mentioned. And I will go here. So you can see all the chain key Bitcoin transactions and all the chain key Bitcoin volume and transactions that exist. But essentially, this is like a digital twin of Bitcoin on the ICP network. And now you're probably thinking, wait, you are telling me wrap Bitcoin is bad, like this is bad, and you're telling me that canisters can receive old and send Bitcoins, the real ones. Why would you have this digital twin again? Why not use directly the native Bitcoins? Well, even if the two networks are connected, and yes, canisters can send Bitcoins and so on, you don't solve the problem that you still have to go through the Bitcoin consensus. So when we do a transaction on ICP, if a canister is sending Bitcoin to another canister, then we need to wait for the Bitcoin network to essentially validate the transaction. And this takes a long time, 20 minutes, 30 minutes. So this integration doesn't make the Bitcoin network faster or better. It's just on the ICP side, we can do things, but it doesn't change the problem of Bitcoin is slow and is expensive. So for big transactions, important transactions, maybe you want to go through the real kind of network. But for the rest, there is something called chain key Bitcoin, and it's more secure and better than this wrap Bitcoin. And I will explain why. So chain key Bitcoin is a Bitcoin native to the internet computer. It's backed 1-1 by real Bitcoins. It's fully transparent. You have 2-second transactions, so you can just send that around anywhere, anytime. And also, it's easily integrable with any application on the IC, following a standard which we've come up with, which is ICRC1. Why is it better? Because you replace this bridge by a canister. So I'm not saying this is perfect, because you still have to trust the ICP protocol, but I personally have more trust in a canister that is open source. Of course, it's open source and you can verify the code for it, that essentially manage this bridge, than a few companies that I don't know. I believe that software and like open source software is the best and the most transparent way to kind of solve this problem. So that's why I would argue that it's a safer solution and a better solution long term. How does it work? There are two canisters on the IC. There is the minter and the ledger for chain key Bitcoin. The minter is a canister that has a wallet on the Bitcoin network. So essentially the same thing as this, you could replace with the canister here. The minter has a wallet. You as a user is going to send your Bitcoin to this wallet. Once it's done, remember that the Bitcoin network is connected with the ICP network, so you can directly check from the minter if this has been correctly sent. If it's correct, then the minter is going to send a mint request to the ledger. So the ledger stores all the transactions and is the canister that is responsible for managing chain key Bitcoin. Once you have that, essentially this is a canister, so you can do transactions from here, and it's super fast because canisters are fast. And you can use that on OpenChat. For example, you can send like Bitcoin directly from OpenChat, chain key Bitcoin directly from OpenChat, and so on. And just to make things very clear, again, it's not a magical solution, but essentially, instead of having a company or an entity, you have a software. So you have a canister that actually in this case, two canisters that manages the bridge. And the code for those canisters is fully open. And that's why I would say it's a cleaner and better solution than using bridges. How do you use that? Well, you can do many things. So you can do crowdfunding on the IC. So you can essentially raise money for a specific project using Bitcoin, so chain key Bitcoin. You can send that on applications like OpenChat and so on, Discover. You can do on-chain decentralized exchange. So this is something that is coming pretty soon. Super interesting. You can buy NFTs as well, like all sorts of kind of marketplace would be able to integrate with chain key Bitcoin. You also have okay, so this one is a bit more complex, but you have what's called non-custodial lending protocol. So you can essentially use your crypto for lending to other people without having to bridge to another network. So you can check it out. It's called Finterest. And yeah, I mean, that's just the beginning. I believe there are way more use cases than that. But 10K Bitcoin has been around for 5 or 6 months, I think. So it's also a pretty new technology. And if you want to take a look into it, it's here. So you have, this is the minter, this is the ledger. So we can see, I hope that, no, there is not the link to the source code. Let me see. Okay, so once again, everything is explained here. What I was looking for is the source code. Okay, it's here. I believe it's used in some places for payments. So Yeah, everything is not. So it's not really a wrap token. And I was looking for code examples. I thought they had here. Mm-hmm. So this is an example with, yeah, Bitcoin. Oh, this is my previous project. You can take a look. It's a NFT. It was an NFT project. Really cool as well. Okay, so they don't seem to have. I thought they had an example integrating chain key Bitcoin, but they only have real Bitcoin and threshold CDSA. So this threshold CDSA, and it's the most complex like thing that I've talked about, but it's also possible to use that for other currencies. So right now it's only Bitcoin, but in a few months it's going to be Ethereum as well. They're working on Ethereum integration, which means you can also do all the things I've talked with Ethereum. So the canisters are able to hold Ethereum and send that around. And you can do that with any cryptocurrency because all the cryptocurrencies are using ECDSA under the hood. This is like the underlying protocol, cryptographic protocol. Some of them are using something different, but 90%, I think 99% of them are using ECDSA. So we could integrate with Dogecoin, Litecoin, and all kinds of currencies. Stable coins as well could be integrated with that because stable coins are from the Ethereum network, most of them. They are just like RC20 tokens. So they could also be integrated with that. And yeah, that's about it. I think what's missing right now with this is more like concrete examples. But as I said, it's really, really early. Like those features have been released only a few months ago. So there are a few developers building it, but I think we need more people diving into those possibilities. What about yeah. Do you have any question? Is it clear enough? I think it's very complex topic, but yeah, I've tried my best to make it clear. So there are really, really good example, which I haven't had too much time to dive into, but it explains how you can build a canister that you can deploy the smart contracts, generate a Bitcoin address, receive Bitcoin, check your Bitcoin balance, sending Bitcoin directly from your canister. So this is pretty cool. Yeah. Yeah, let's follow up with the documentation. It's I need to do a better job with this as well because there are a lot of resources for those Bitcoin integration. But it's also hard to find sometimes. They are in different places. So I think yeah, I think if you find good resources, make sure to share it in the chat. And I'll also do my best to dive into those examples. Okay, thanks everyone for being there to this morning. This afternoon we have the WebSocket discussion. So it's pretty exciting because I think it's the first time that we have someone outside of Dfinity. So someone from the community that is basically contributing to the core protocol. That's something I want to see because it's important to have many contributors. And so yeah, this is those are Massimo and Luca. They were also in the one of the first bootcamp, and now they are building something called WebSocket on the Internet Computer, which they will explain way better than I can do. So see you everyone this afternoon, and good luck with your projects.